Hello, everybody. This is Professor Hudson Zanin. I'm from University of Campinas, and this video I'm going to deal with two things. One is to present the proposal I'm going to submit to FAPESP on the Young Investigators Phase 2 call. And also, I'm looking for partners, myself and the group research we have. So to develop the technologies, I'm going to very briefly discuss here. In less than 10 minutes, I plan to give you guys the idea what are our plans. So basically, for mobility, we plan to develop two technologies, the lithium-ion and lithium-sulfur batteries, which we plan to encapsulate in pound cells and cylindrical cells, and then produce modules. Then we also, for stationary solutions, plan to develop the redox flow batteries. So there's a link here I'm going to put in the description of this video about the manufacturing we have here, the pound cell lab scale manufacturing of this kind of cell. So, and then we are looking for partners to make this project even greater. So if you are releasing this, probably you have access to the proposal, and then yeah, that's the idea. Let me see if I can explain properly our plans. So these two technologies, the lithium-ion and lithium-sulfur batteries, are the most interesting technology for power, especially lithium-ion system, and for lithium sulfur, we have higher energy batteries, much higher energy batteries density. Okay. So same higher amount of energy with same volume of the cell. So basically, in all kind of system here, in both kind of system, we plan to start in a coin cell, which is basically a coin that we plan to use to reduce cost on the preparation of the best electrodes and electrolytes. So this is a tool to investigate in a real device materials. So we plan to study different types of carbon-based material, metal oxide, spinels, even lithium metal, to see if we can use different types of electrolyte, especially from aqueous to organic, but also moving towards have all solid state system. That's the main goal here from both technology here in this proposal. So we want to reach after a 5-year project, a very good lithium ion and sulfur batteries, all solid state system that we plan to put in a pound cell. This is a rectangular cell you're seeing here in the both picture, the middle, center, and the cylindrical cell. We plan to, we already have the setup for the pound cell preparation, and this proposal we plan to establish a facility to produce the lab scale manufacturing of the cylindrical cell. So we plan to certify the cell, so do some thermal runaway tests, short circuit, vibration, pressure test in vacuum, for example, for high altitudes, and lots of different types of important tests that is important for certification, especially in the mobility for electric vehicles. So after this phase of certification, we're going to associate the cells in a modules to have a higher voltage output and high current. Let's say the target here will be about 300 volts and 100 amps, at least 100 amps. Okay. So this is the ideas we have. There's some next slide. We're going to show the details of what electrolyte going to use and electrodo and this kind of things. And the letter B, the part B here is to present the redox flow batteries. So for stationary solutions. So that's the both designs here is what we have in the lab scale. In the bench top, we have two containers separated by a membrane. So redox flow is different from conventional batteries like lithium-ion, for example, because there is no intercalation like in lithium-ion. There is no process that relates to conversion, for example, lithium sulfur, for example. What we have here is the oxidation and reduction of the electrolyte, which are pumped. For example, here we pump the electrolyte different containers. And then when we come back, we reverse the system, we extract current from this. So we oxidize using the current from, for example, a solar panel or the turbine for ionic park, for example. And then we store this in oxidized and reduction electrolytes that we can pump back and have this part of this energy recovery. The system is now commercially available, and the efficiency of this kind of process is about 8%. Okay, so the main target here is to replace vanadium, which is the main element that have been using quite a lot in this kind of system. But there's lots of alternatives like iron, chromium, cerium, for example, zinc, which is much cheaper than vanadium. And to reduce costs here, we need to attack the electrolytes and the membrane. So we plan to replace vanadium for these elements I said, but also the Nathian membrane is extremely expensive, one of the most expensive part of this kind of system, which we have kind of an interesting solution for it. Like, for example, we diluted the solution of Nathian and then make a very thin film in a mesopore membrane that is selective for different ions. So that's important to play here with the membrane. And if we succeed, we have about $100 per kilowatt water in a container size. That's the size we plan to have here in this project after the 5-year project. Just to summarize, so I presented here first the image because the image say much more than words, but in words here, what we have is we play with electrodo materials, electrolytes, and a coin cell size, and then we go into move for basic science studies, for example, operando, electrochemistry, analysis, and some simulations to understand the failure, to understand the work window voltage of the cell, and how much we can cycle the cell. Also, we plan to, after we decide what is the best option for both materials, for all the materials inside the cell, we plan to prototype this in a pound cell in a cylindrical cell level. And also, after certification in the cell size, we're going to do some assembling. We're going to assembling the cell in a level that we could have higher current and higher voltage from the modules. So we plan to develop the battery management system, the control, the intelligence of the software to recognize the cells in a different level. and then take actions to make everybody work together in the same way. So then we're going to certify the modules the same way in vibration and heating, on pressure, all this kind of important impact that are important for electric vehicle. And also for mobility, we're going to have this redox flow system. We're going to start first the electrolyte in the benchtop level. So we're studying electrolytes, membranes, and then we're going to start moving for a more engineer level of issue, for example, pumping the cells, seeing the effects of pumping faster, lower, and charging faster and lower. And there's something I didn't say here. I write in the manuscript and the proposal, which is basically we can, in this kind of system, we can separate charge from power, which is basically we can have smaller or bigger container size, and have a smaller or a higher amount of energy. And if we want to have more power, we must have much higher electoral, or if power is not a big issue, we can have reduced size or a less amount of electrodes. And that's a very important. This is a very good picture of this kind of system, and we're going to explore this a lot. So then, after have this benchtop analysis, we're going to start assembling the cells in a container size in a modular way. So prepare some modules and then produce, aiding them to have a higher voltage and a higher current. And then, of course, we need to control all the cells to work together. All this kind of system, we want to reach a technology readiness level 8, which is almost in a commercial level. Of course, then we need to pass to someone to produce this. So we have here writing. So if you have the proposal, it's much easier to read. Just give you guys a thought here. This kind of target right here for lithium-ion, and also to explain the difference between the lithium-ion in a liquid stage, which we have the membrane, we have the electrolyte separate in the cell. But when we have this all solid state system, everybody's much closer together, because the electrolyte, we are talking about a micron, 2 micron, maybe 3. The thickness of the electrolyte is much smaller, and then the system can have a high power as well. So basically, all this kind of system have been said, and I'm not going to read all this. Can read it by yourself on the manuscript. All this kind of material we propose to use. Here, that's a picture of took from internet to give you guys the idea what we plan to do. We plan to produce modules that we can aid a different amount of these cells in the container, and then it's good power a fuel house same time. Building has a big backup, or let's say automate power system. And there's here in blue the control of the system. So basically, the main idea is to replace, in this project, to replace vanadium and reduce cost by finding better membranes, and have the first Brazilian redox flow system here prepare all in this country. And of course, in the modular and the other types of battery, I guess, will be the first time here producing Brazil as well. So basically, what we ask for FAPESP is pay human resource. We are not allowed to ask for a PhD, which would be great, but it's not allowed here in this proposal. And then we request, in that case, 8 master students. We're going to put about 0.5 million reals here in this scholarships. Well, we're going to employ 1.5 million reals for manufacturing the cylindrical cells, and that's very important because we have been talking to several car manufacturers, VW, Fiat, and Caoa, for example, and these guys are definitely looking for models that have cylindrical cells in this system. Much easier to make the interface, bring this kind of technology inside the cars than pound cell. Pound cell is very important for tools and other kind of system for smartphone, for laptops, let's say, and the manufacturing, the beginning of the manufacturing, the pound cell is much cheaper. But here we believe that with this new and very important strength pushing us for the new types of cars, EV cars or hybrid system, we're going to need this kind of manufacturing. That's why we're requesting here as one of the main expenses of this project. We believe that's going to put us on the roadmap for the route 2030 for cars, for electric vehicles in Brazil. So also we have some amount of money put on the consumable and refurbishing the labs to adjust and make safer to avoid any incidents. And also we have this 0.4 million reals for technical reserve. This is something FAPESP always puts for, let's say, a flexible cash you can use as you wish, as the project needs. So, so we are thinking that we could improve this amount of money, maybe asking and co-funding this project and bring, for example, PhD students. Let's say every master student, there's his own activity related to the project. If we can have an extra PhD student doing the same or similar work, expanding or reducing risk in every single activity we wrote in the main proposal, that would be very good and bring more stability and comfortable for us that are going to managing the system, the project. And of course, this amount of money for consumable are smaller than we need, and we are looking for partners to make this bigger, to produce more cells, different types of cells, and try different types of electrolytes, and to boosting time and make it faster. Okay. But of course, in a lab scale production, we have some waste we do not have in very, very small, let's say, coin cell size cells. So for pounds and cylindrical, we believe that the amount of consumable will be slightly higher. Then we believe that is important for us to have this extra funding. So basically, the partner is going to fund human resource and the consumables. So we're looking for another 3 million reals and productive service. So to close the energy transition program we have here at UNICAMP are aligned with the roadmap for several companies. We have been shared with them, let's say VEG, Mali, um, uh, Vale, Petro, and other total several companies that we have been discussing about the future of the roadmap they have for bringing new technologies to light. Okay, and there is a project that we have been submitted and almost approved, not finished yet, to FINEP, which is related to a hybrid car that use ethanol and a fuel cell to convert and produce electricity to the system and to charge batteries and to move electric motor. And then we have a car that have onboard generation of electricity, and they use ethanol from the infrastructure we have here to have the carbon neutrality, that is very important for the next generations and to reduce the global warming. So our roadmap are related to this technology we discuss here in this very short presentation, the different types of batteries for stationary and mobility. That's all, and thank you very much for watching, and please do not hesitate and email me or any message. So the email and the mobile number is on the beginning of the presentation. Bye.